Alright guys, so this is our first video for our Flip the Classroom lesson on polynomial functions of higher degree. In this video we are going to talk about the graphs of polynomial functions. And in general what we're going to say is the degree of the polynomial gives us the general shape of the function. One way that we see this is that a polynomial of degree n is going to have at most n minus 1 extrema, right? So we're going to take a look at some general cases here. And in all these general cases, we're going to say that our lead coefficient is a positive number, right? So the first case we'll look at is the linear function. This is a polynomial of degree 1, and that means that we would have 0 extrema. It's a pretty simple case. So we've got a positive lead coefficient here. That means we've got a positive slope. And if we draw a linear function with a positive slope, it might look something like this. Here we don't have any contours, it's just a straight line, right? So we don't have any maxes or mins, and then clearly that means no extreme, right? If we look at a quadratic, we can say here that we have a degree of 2, which would give us 1 extrema. If we look at the most basic case, we've got y equals x squared, right? And that is the parabola with its vertex at the origin. And now clearly we can see that we're getting the extrema of a min at that vertex, right? Now, we may have other terms that shift our parabola around the xy axis. But in general, we can see wherever that parabola has been shifted to, we're going to have the extrema at that vertex. All right, so looking at a cubic, we would say that we have a degree of 3. And that would give us at most 2 extremes. Now, in the case of the cubic, right, if we're looking at y equals x cubed, the most basic case, we would see a graph that looks like this. Basically coming up from negative infinity, flattening out at the origin, and then going up to positive infinity. And right here, basically what we can say is that this graph has no extrema. So when we say at most 2 extrema, we're really saying 2 extrema or no extrema, right? If we look at y equals x cubed plus x squared, though, we see a graph that looks a little bit like this. So it looks like that cubic, but sort of shifted a little bit onto the negative x-axis. If we take out our calculator, we can type this guy in and see the graph that we're seeing right there. If we zoom in, what we're basically going to see here is a max between negative 1 and 0 and a min at 0. And basically what we're seeing here is on the interval between negative 1 and 0, the squared terms are going to be more positive than the cube terms are negative, right? So looking at our two basic functions, we can say that right here for y equals x cubed, when we have negative x values, our cube is negative. And for y equals x squared, when we have negative x values, x squared is positive. And that interval that we zoomed in on, from negative 1 to 0, is basically the interval where the squared terms, right, are more positive than the cube terms are negative, giving us a conflict between these two terms, right, which accentuates the contours of the cubic, right? It draws out the contours of the cubic, giving us our max and our min. And in general, basically what we can say is that the conflict between the terms in a polynomial is really what is giving us the max and the min. In the end, the highest power term, right, is always going to control where the function goes as x goes out to negative infinity and positive infinity, right? But there are going to be intervals where these other terms have greater values than that highest power term, right? Now, when we involve more terms, we're going to see more conflict between the terms, giving us greater contours and more accentuated maxes and mins to our polynomials, right? And so we may, if we involve more terms, we may actually see a cubic that we don't need to zoom in on to see the max or the min. But in general, what we want to think is the reason we're seeing these maxes and these mins in these polynomials is because of the conflict between the terms, right, giving us a more pronounced contours. For a quartic, right, we would say that we have a degree of 4, right, and that's going to give us at most 3 extrema. Our most basic case is going to be y equals x to the 4th. And right here, if we graph this guy, we basically look like a flattened out parabola. Now right here, that at most 3 extrema is going to mean 3 extrema or 1 extrema, right? Because in our most basic case, really all we have is a min, right? But again, if we get more terms involved, we're going to see our contours more pronounced. And basically what we can say is that a quartic is going to have all the same contours of a cubic, but in the end, because that highest powered term has an even power, right, it's going to take negative numbers and make them positive, and so it's going to take the function values up to positive infinity. Now right here we're seeing all 3 of the possible extrema, right? But it could be that we see more pronounced contours and we don't get all 3. So right here we could see the first 2 extrema maybe not as pronounced, right? And basically what we would see there is a graph that looks like this, where again we have just the 1 extrema, right? If we're looking at a quintic, we would say that it has a degree of 5, and so we've got at most 4 possible extrema. The most basic case, we've got y equals x to the 5th, and that's going to give us a graph that looks like a flattened out cubic. Now in this case, we would say that at most 4 means 4 or possibly 0, right? Now again, if we get more terms involved, we're going to get conflict between the terms, giving us more pronounced contours, creating those maxes and mins. And what here we can say for the quintic is we're going to see all the same curves that we see for the quartic, but basically in the end we're going to see function values go down to negative infinity, right? Because that highest powered term has an odd power. So when we raise negative numbers to odd powers, we get negative numbers. And because these numbers are going to be larger than any of these numbers, right? That means when x goes out to negative infinity, our function goes down to infinity. Again, right here we're seeing all of those extrema pronounced, all 4 of them, right? But in general, we might see a case where we don't have all of these extrema pronounced, right? So maybe our first 2 extrema, right, are not pronounced. And basically what we would see here is a graph that might look something like this. Now, in general right here, that would be giving us just 2 extrema. So when we say at most 4, we mean 4 extrema, 2 extrema, or 0 extrema. Now, in general, one thing we want to see here is if we take away 1 extrema, right? If we're basically saying that our contours are not going to pronounce one of our extrema, then really we're taking away 2. Because if I sort of bring down that max so that it's no longer a max, really I'm taking away the contour that gives me the min as well, right? So basically if I flatten out that max, I'm seeing something that looks like this. And so when I take away 1 extrema, really I'm taking away 2 extrema, right? In general right here, that's going to be true for all these polynomials, right? And we're sort of seeing that with our quartic as well, right? We took away the 1 extrema here, the min, and basically we saw that graph flatten out, giving us just 1 extrema then, which was the exact case that we saw down here. In the case of the cubic, right, when we take away 1 extrema, we're taking away 2 extrema, and that gives us 0 extrema. For the quadratic, it only has 1 extrema, and it's always going to look like a parabola, so we're never going to see negative 1 extrema from the graph of a parabola. In general, one of the things that we want to take notice of as we're looking at polynomials of even and odd degree is trends that we're seeing in the end behavior. So even degreed polynomials and odd degreed polynomials create certain patterns in the end behavior, right? So in general right here, what we can say is if we're plugging in x values going out to positive infinity, right? For all of these functions, for all parabolas really, if we've got a positive lead coefficient, what we can say is that when we raise positive numbers to whatever power and multiply them by a positive coefficient, we're seeing that highest power term go to positive infinity. So whether our degree is even or odd, we can say that the limit of f of x as x goes to positive infinity is going to be positive infinity. However, when we take a look at x going out to negative infinity, we're seeing a different trend here, right? With the odd degree polynomials, right, we're basically seeing negative numbers raised to odd powers giving us negative numbers. So that highest power term is now going to be negative as x goes out to negative infinity, and that's going to take our function values down to negative infinity as x goes out to negative infinity. So right here, for our odd function, we're going to say that as x values go out to negative infinity, function values go out to negative infinity. Whereas for the even degreed polynomials, right, we're seeing that highest power term with an even power. And when we raise negative numbers to an even power, they become positive numbers. So that highest power term, right, the greatest, the term that it's going to generate the greatest values is going to go up to positive infinity, and it's going to take the whole polynomial with it. And so we can say that as x goes out to negative infinity for an even degreed polynomial, we're going to see the function values go to positive infinity. Now this is specifically for cases where we're looking at a positive lead coefficient, right? But this is a trend that's pretty true for all polynomials. So we can take a look at the lead coefficient, right, and the degree of the polynomial and immediately be able to determine the end behavior, right? If that lead coefficient is a positive number, right, we're going to say that an even polynomial is going to be going up to positive infinity, right, as x goes out to negative infinity and positive infinity. And with an odd degree polynomial, we're going to say that the function values are going to be coming from negative infinity as x comes from negative infinity and going to positive infinity as x goes to positive infinity. Now, in general here, what we're going to be able to say is that that is always going to be the case when the lead coefficient is positive, right? But when the lead coefficient is negative, we're going to see that behavior flipped. So one way we can think about this is for a positive lead coefficient A, we will see the equation be right side up, right? So it's basically seeing that behavior that we observed on the last page. And if the lead coefficient is negative, we will see that behavior upside down. So basically we'll see the end behavior flipped, right? So right here, if I'm looking at A, right, that is an odd degree polynomial with a negative lead coefficient. If it were a positive lead coefficient, I'd be coming from negative infinity and going to positive infinity. But since I'm seeing a negative lead coefficient, I'm seeing that behavior flipped. So as x goes out to negative infinity, my function values are going up to positive infinity. As x goes out to positive infinity, my function values are going down to negative infinity. And we're seeing that in the graph of the function as well, right? If we look at this next example, g of x, right, we've got 1/2 x to the fourth plus x cubed minus 5x squared plus x minus 3. And right here, we can see clearly that this is an even degree polynomial with a positive coefficient, lead coefficient. So basically right here, we're going up to positive infinity as x goes out in both directions. And that can be easily determined by the graph as well. But in general, we can see it really just in the equation itself, just by looking at the lead coefficient and the degree of the polynomial. So what I want you guys to do is to go ahead and try some of these on your own. You guys can try these two guys. Should be pretty quick work, and we'll come back and look at this in a second. All right, so looking at our first function, we've got f of x equals negative 18 x to the fourth plus x cubed plus 27x minus 125. Our degree is even, right, that highest power of 4, and we've got a negative lead coefficient. So we're seeing the end behavior of positive infinity and positive infinity flipped. And now as x goes out to negative infinity, our function is going down to negative infinity. And as x goes out to positive infinity, our function is going down to negative infinity as well. So looking at this next guy, right, we've got a highest power of 7 and we could say that the lead coefficient would be a positive 1. So our function values are coming from negative infinity as x comes from negative infinity. So basically right here we're going to say that as x goes out to negative infinity, we see the function values go down to negative infinity, and as x goes out to positive infinity, we're seeing our function values go up to positive infinity. Okay, so that's this one. Our first video is done, and we will see you guys on the next video.